Hello, I want to talk about the Graph Lab. The Graph Lab is due on April 17th, Friday, and that's because the last couple of pages, I think there are 8 pages total in the Graph Lab, we won't introduce the approach for finding topological ordering until later on next week. So let's look at page 1, item 1. So here's an expression of the state graph. Now it's called a state graph. That means this graph of the U.S. states. It doesn't mean the graph of the state of the graph or something like some other phrase. It's a graph of the U.S. states. So the representation has V, the vertices, and it lists out a number of states. And then it lists E, a number of edges. Now we don't know, it doesn't say directly whether this is a directed graph or an undirected graph, but it's obvious that it's a directed graph because the two edges, Hawaii to Texas and Texas to Hawaii, go the opposite directions. And so it is a directed graph. And so every state, the first state is the start point and the second state is the end point. So first of all, draw the graph as a graph. And the nodes, you can use the first letter of the states because they happen to all to be to have this disjoint set of first letters. So you could use the first letter of the state or the whole state name and draw the graph, first of all. So to do that, you'll use the vertices and the edges. And then the numbering is a little bit off, but oh well. So describe the graph pictured above using the formal graph notation. Now this is just the same as this discussion up here. So this is not a really intensive question because you've got it right above it. So then question 2A, is there a path from Oregon to every other state in the graph? So you look at Oregon, and this is a yes/no answer, true or false. And remember that you can't go opposite a direction, an arrow. So is there a path from Oregon to any other state? To any other state. In other words, if not, then this is a disjoint graph. Is there a path to Hawaii to every other state? So again, that's a yes or no question. So you gotta look at it, look at the graph and figure it out. And from which states in the graph is there a path to Hawaii? There may be several paths that go to Hawaii, several states that link directly in one edge to Hawaii, or maybe only one. Or maybe none at all. Okay, so now on page 2, this page. So still using the same graph above, the state graph from page 1, show the adjacency matrix and store the vertices in alphabetic order. So again, these states all begin with a unique letter, so they will go into alphabetic order easily. You could use the first letter of the name of the state, especially along the columns, since you'll want to do that. So show an adjacency matrix. Remember the definition of adjacency matrix from the previous video. So now this is the alternate way of representing this graph, showing the adjacency lists that would describe the edges in the graph. So again, you have the edges in an array, or maybe a list, but probably an array. And then from each edge, from each state, each vertex, there is a linked list of edges. Okay, now, page 3, question 4. Different graph. This graph right here. Okay, this graph does not apply to the state graph on the previous slide. It applies only from here down. Now, what I'm going to ask you to do is to put on your SAT hat and say to yourself, okay, I can eliminate the obvious ones. What do I, and as I go down the list, I'll eliminate others. And so there will only be one at the end of each of these 4A and 4B. Now, the question 4A says list these graph nodes in depth first order beginning with E. So it tells you which node to start with, E. And there's obviously question B drops out right away because it doesn't begin with letter E, vertex E. And you'll have to go down the list and see which ones do the depth first searching and which ones eventually fall out. Same thing with 4B, except this is breadth first order. Remember the difference between depth first and breadth first. Depth first looks at the descendants of a node first. And it could look at all the descendants. In the case of this graph up here, it could go all the way down so that there are no more siblings, and then looks at the siblings next. The opposite is the case of breadth first. In breadth first searching, you look at the siblings first and then the descendants. Okay. Now, notice the word distance is underlined. I don't care how it gets from Atlanta to every other state, how you get from Atlanta to Denver. I just want to know the distance, the shortest distance. So now, in theory, you could wait until next week's videos and look at the shortest path algorithm. But frankly, you could do it brute force just by calculating the various ways to get from one city to another. Now notice, so basically what I want is Atlanta to Houston. That was an easy one. It's 800 miles. So Atlanta, Houston, 800. That's all I really want. Or just Houston, 800. And the same thing with all the other cities in the graph. Okay, so now we want to find a minimum spanning tree using Prim's algorithm. So I talked in detail about Prim's algorithm on the previous video. It says to use 0 as a starting vertex, so that will help us to be able to follow the steps that you did. Use Prim's algorithm. And then in the next page, page 7, it says, it gives you exactly the same graph and asks you to find the minimum spanning tree using Kruskal's algorithm. So show again the weights and the steps. You have to come up with the same minimum spanning tree, since the edge weights almost all unique, not these two, 0 to 2 and 5 to 4. But trust me, it'll be unique. And then find the minimum spanning tree of this algorithm you could list it out here, since you're going to be submitting this online. In the past, people have used their pencil to weight in the paths, but you're not going to want to do that. Maybe you'll bold them in, put in another path or something like that, or perhaps list out the minimum spanning tree using either algorithm. And start with Minneapolis-St. Paul. Just so, again, not that it changes the minimum spanning tree, but it should change the order. It should change the ability of us to see what order you did things in. Now, pages 8 and 9 are the ones that we haven't covered yet and we'll cover next week, and that's topological ordering. You could think, if you look at number 9 and at page 9, number 10, you'll see this is basically the prerequisite listing of, as you're all familiar with, by scheduling out your own courses. These are not our courses, but they're similar. And so, for example, discrete math has got to come before programming 2, but could come in parallel with programming 1 or computer organization or operating systems, but has to be before senior seminar because programming 2 is before high-level languages, which is, anyway, you get the picture. So there is a specific algorithm for finding the topological ordering, and that's what we'll ask you to do for step 9, page 8, step 9. Okay, so that's the graph lab, and you are welcome to start it now. It's due Friday, April 17th.